Hi folks, Mr. Long here. I'm creating a screencast right now to introduce you to the derivatives of exponential functions. And it's a fairly straightforward way to do it. We're going to look at exponential graphs and look at what's called vertical scaling. You might have called it vertical scaling. You may have called it vertical stretches and compressions. You'll often see university profs refer to it as scaling. Things get scaled up or scaled down, or a scaling factor. So let's look at, let's start with this one here, y equals 2 to the x. Okay, and let's see what happens. We're going to transform that. So 2 to the x, by the way, 2 to the x, I can write it a couple of different ways, right? I can just write it as y equals 2 to the x, or I can write it as 1 times 2 to the x. You may remember writing these as y equals a times b to the x, where a is the y-intercept. So if I think of 2 to the x as 1 multiplied by 2 to the x, we call that the unit identity. Multiplying by 1 doesn't change anything, right? So we can think of it, when I see 2 to the x, what I immediately imagine is 1 times 2 to the x, and that gives me a y-intercept of 1. And it's a exponential growth function, it's a doubling function. So what happens now if I change that a value to 0.5 over here? So look at that. Now I'm going to make a 0.5. Well, I'm multiplying all of those y values. So the way to think of this, folks, is you really want to think of this as 2 to the x being scaled by 0.5, right? So it's 0.5 times 2 to the x, or 2 to the x times 0.5, because remember that multiplication is commutative. The order of multiplication doesn't matter. So I see that as 2 to the x being scaled by 0.5. So that means that every y value on 2 to the x, the new y values for this function, we just take 2 to the x and we multiply by 0.5. So we get a function that has a y-intercept of 0.5, and it's always going to be half of 2 to the x. So that's 0.5 times 2 to the x. Then if we look at this one at the far right, now what happens? Well, now I've got the a value is now 3. So I'm taking 2 to the x, and I'm scaling it vertically by a factor of 3. Okay, I'm vertically scaling it by a factor of 3. So that means that everything is going to be, on the new graph, is going to be, the y values are all going to be 3 times that of 2 to the x. So what does that look like? Well, it's always going to be 3 times higher, right? So it's going to go like so. All right, so if I take any vertical line here and I compare those two values, the red one is going to be 3 times the black one. Okay, if I take this one here over here, now I'm going to go far to the left. Now the red one is 0.5 times the value of the black one. Okay, so that's what it is. I think of it that way. So a vertical scaling. All right, so that's our review that we've done. It took about 3 minutes. Now what we're going to do is start thinking about exponential functions and their rates of change. A really great for this is Desmos. So we can go to Desmos, and what we can do is take a look at a little series of graphs that I created, and we're going to graph 2 to the x, which you see right there, and then we're going to graph the derivative of 2 to the x, f prime of x. So what you see here is, what do you notice? You notice that so the slope around the y-axis is, for the red, which is 2 to the x, is positive, and it's sort of small. Well, look at that. The blue graph is the derivative, right? The dashed line is the derivative. The dashed line is the derivative, and that's a little bit smaller, but positive. Then you get up here, and well, the slope of the red, which is the blue y value, that's positive and getting bigger, positive. So again, the value right here is the value of the blue dashed one is the slope at the same x value, and so on, right? So if I was to draw a tangent up there, it's getting much, much steeper, so that means the value of the tangent, the slope of the tangent rather, is also increasing. So we see that the derivative of an exponential function looks like just another exponential function. And what you see here is that what I did was whoops, it easy. I gotta get into there. Oh, sorry, folks. Whoops. And oh, there. So I have to come down here, and I need to do that one, and that one, and that one, and that one. Sorry, I just had to turn some things on. So, what do we have here? The red graph is 2 to the x. The blue dashed is the derivative of 2 to the x. The black line is just an x value. So if you look at this, what you see is you can see the y value on both the 2 to the x graph, which is in red, and the y value at the same x value for the derivative. So if we notice, the derivative is always below the function for 2 to the x. Okay, so that means that the slope, remember, so this number, this 3.9 number that you see, okay, the 3.9 number that you see right there, that number is the slope. Okay, so that's the slope, and at an x value of 2.5, that's the y value. So what I wanted to do here, if you notice, or what I did do is we divided all of those values. So I have to go back to the graph here. And on the graph, if you notice, I did f prime of a divided by f of a at every x value. So if you take a look, you'll notice that it's 0.693. It doesn't matter. It's a constant value. Okay, so 5.1 divided by 7.4 is 0.693. 2.77 divided by 4 is 0.693. And it's always a constant value, right? It's a constant value. So again, that comes right here. So that is when I take the derivative at every single x value. A just means I can use a slider and use any different x value. And then I divide it by f at a, I always get the 0.693. So again, when I take the slope of the tangent and I divide it by the y value of the original curve, I always get a constant of 0.693. Well, that's just going to be the tangent slope, or sorry, that's going to be the scaling factor. So let's take a look at this. So what I'm going to do now is go back here, and I always have to restart these graphs. So what I'm going to do now is just restart this, and we're going to use a special function, which is 2.7183 to the x. So if you notice, so that's the function right there, and then now I plot, well, I've got the function there, that's the derivative now, g prime of x. So isn't that interesting? I'll just maybe make that dotted. So there's the derivative, there's the original function. You can actually just see the dots now above, or right overlapping g to the x. So that means that if I have a function, an exponential function that's 2.7183 to the x, that the derivative is the exact same as the original function. They overlap, they coincide. And that makes sense too with this calculation, because look at the calculation here. G prime at every single x value divided by the original function at every x value gives you 1. Okay, so that means if the derivative divided by the original function is 1, what's the only time, when you divide something and you get an answer of 1, what has to be true about the numerator and the denominator? That's right, they have to be equal. Okay, so g prime of a over g of a is 1. Okay, so let's go back to, now that we know that, so I think I have to restart this again. Oops, a daisy. Okay. So what I'm going to do now is I'm going to go to 3 to the x and see what happens. So h of x is 3 to the x. And then I need h prime of x, which is, did h prime of x disappear on me? Oh, it looks like it did. Okay, that's fine. We can do h prime of x. So we'll just do this. Notice now if I zoom in, and I should have h prime of x as the dashed line there. So our prediction is true. So now the derivative is greater than the function value. Okay, so the slope is greater. So for example, if you had bacteria growing at a rate of 3 to the x, or not at a rate of, if the equation was 3 to the x, if it was tripling, then that would mean the growth of bacteria would be more than tripling. Okay, so if something is tripling, then that means that, and you're at 1,000 bacteria, that means that the growth rate is pretty close to, or actually if you're 100 bacteria, it would be about 110. And so we can see that from here. So look at this, h prime of a over h of a. So that means any derivative value divided by the original function value is always 1.0986. Okay, 1.0986, which is, so 1.0986. So now let's go back finally. So as the last thing, we're going to go to here and see what we've got. So for 2 to the x, the original graph looked like this. Okay, that's 2 to the x. And then the derivative looked like this. It was the dotted one. It looked like that. Okay, and if we notice, what we did was we did y prime over y, which is f prime. So when we took the derivative and we divided it by the original function value at every single one, we got 0.693. So what does that mean? Well, that means that y prime, if I multiply both sides by y, I get 0.693 times y. Well, that means y prime equals 0.693 times by 2 to the x, because the original function was 2 to the x. Okay, so that, folks, is the derivative of 2 to the x. Okay, it's a vertical scaling. That's all it is. So the derivative of 2 to the x is a scaling down by a factor of 0.693, because when you multiply something by between 0 and 1, you're going to get something smaller. Okay, so we can go back and look at Desmos, but what I'm going to do is I'm going to share with you, well, we might as well do that. Let's go back and look at Desmos. Back over to here, and we could draw our 2.7183 to the x, 2.7183 to the x, and then we can draw the derivative. Well, what is the derivative? It's right over top of it. It's right over top of the function. Okay, they are the exact same. So we know that that equals 1. So if I look at that, y prime over y equals 1. Y prime equals 1 multiplied by y, or y prime equals 1 times by 2.7183 to the x. So that's interesting. So that one's not vertically scaled at all. So the derivative is equal to the original function. So if the y value is 1,000, the slope is 1,000. If the y value is 1,000,000, the slope is 1,000,000. Now, if we look at a pattern here, if we notice, so when you have 2 to the x, the derivative is below. Okay, the derivative is below. Then when you have 2.7183 to the x, the derivative and the original function are equal. So what's the pattern here? What's the pattern? So it's below, then it's equal. So if I now go to 3 to the x, what's going to happen? So from 2 to the x to 2.7183 to the x, the slope gets closer to the tangent value. And in fact, at 2.7183, it equals the tangent value. So if this pattern is true, then I know what has to happen is this. I would think if the pattern continues, so there's 3 to the x, what should happen is there should be a scaling up now instead of a scaling down, right? If you look at the pattern. So it starts, the slope is below, the slope is equal, the slope is greater. Let's see if that's true. Let's go back to Desmos. Oops. Let's go back to Desmos and see. Nope, we're going to go right there. And we could see that this was now 1.0986, so 1.099. So I'll just continue this on here. Multiply both sides by y. Y prime equals 1.099 multiplied by y. But what's y in this case? 3 to the x. Okay, so we've got a scaling factor. So there's got to be something significant. So if you have 2 to the x, the scaling factor is 0.693. If you have 2.7183 to the x, the scaling factor is 1. The derivative is equal. And if you have 3 to the x, the scaling factor is 1.099. So there has to be something special about this. So, and 4 to the x, of course, would be even steeper, right? We need to talk about this because this is really the important one, right? That's the one where the slope is the exact same as the original function. This 2.7183 is actually not 2.7183. It's 2.7183 ... It's a number just like pi. You know how pi is 3.14, but then there's an infinite number. That's pi. Well, this number here is a special number called E, Euler's number. I used to say Euler's number, but it's E. It's called Euler's number, and it's 2.17183 ... forever. It's an irrational number. It goes on forever. So what we have is that if we have the equation y equals 2.7183 ... to the x, we actually write it as y equals e to the x. And a nice thing about this that really is cool is that d by dx of e to the x is just e to the x. So if I know there's 1,000 bacteria and it's growing by if the equation that governs growth is 2.7183 to the x, I know that the slope is also going to be 1,000. Okay, and we also found out here that d by dx of 2 to the x was 0.693 times 2 to the x. And we also found out that d by dx of 3 to the x was equal to 1.099 times 3 to the x. Okay, so there is something significant that we're going to find out about these numbers, but that comes at another time. Okay, so we're going to stop there. The big idea here is that d by dx of e to the x is just e to the x. The other big, so I guess there's two big ideas. The second big idea is that the derivative of an exponential function is just a vertical scaling of the original exponential function. Okay, so again, I would pause, rewind, go over all of these, go back and forth. And pause, rewind, as I said. Make some notes. You should always make some notes as well. Okay, have a great day.